In this video, I'm going to talk about main sequence stars and the evolution of stars. Like always, I'm going to start with a bit of theory, and then I'll give some worked examples at the end. Please read the success criteria I plan to cover in the video. Before we get started, let's just have a quick reminder about fusion of stars. I have another video about this. We've got here that fusion occurs in the core of the star, and it starts off with 4 protons and they combine in a 3-stage cycle. We call it proton-proton cycle. And as it does that, it also releases energy, some beta positive particles and some neutrinos. And so we have an outwards radiation pressure and some thermal pressure pushing outwards. And that's going to be balanced with the force due to gravity pulling everything towards the center. And in a stable star, these two things will be equal. Newton's first law still applies here. Now I've got a diagram here. We call this a Hertzsprung-Russell diagram. It plots temperature versus luminosity of stars. And notice that this here is actually the greatest temperature, and this is the lowest temperature over here. The fusion process that's mostly happening inside the core is going to be going from making hydrogen to form helium. As we get further in the evolution of stars, you'll see that we can get to other forms of fusion. But these ones are still the protons turning into helium. The mass of the star will affect its possible processes that are going to happen. And what we're going to find is the greater the mass, the greater that gravitational pressure being pulled in, because we know that has to do with mass. And it also then will affect fusion because those particles are going to be closer together, more likely to combine, and increase the amount of fusion. So looking at that in a little bit more detail, the greater the mass, as I said, will have the greater the gravitational pressure pulling it in. Those then will make our particles closer together, increasing the rate of fusion. The more fusion I have, the more of a higher temperature, because that is going to be giving off more energy, but it also gives off more light. That's one of the types of energy it gives off. But it also has a shorter lifetime, since that means I'm going to use up my fuel faster. So let's take a look here at our evolution of stars, and you'll usually see a diagram similar to this one. So I've got here, I'm going to start off with a protostar. Well, what do I mean by that? Basically, in an area that we have high density gas, mostly hydrogen, we might call this a nebula, they're going to start becoming attracted together. Why? Because their masses and masses are attracted. What it does is bring them closer together, and this eventually will start increasing its temperature as well. And at some point, it's going to get hot enough for our proton-proton fusion, which is that hydrogen coming together to make helium. And once that starts to happen, we have our main sequence stars. Now from there, I could have 2 different things going on. And again, it's based on its mass. So this is M with a little circle and a dot in the center. That little circle with a dot means the sun. So stars that are smaller than 8 times the mass of the sun will typically go in this direction. So let's think, what's going to happen to our main sequence star? Eventually, fusion is going to slow down because we have less and less hydrogen in our center. That will be the fuel in the core, not necessarily the shell on the outside. But as that fusion slows down, I will have less radiation pressure pushing it out, causing the core to start to shrink because the gravitation pressure is still there. If it gets high enough temperature, I can possibly go from helium then combining to make carbon or oxygen, but that will then cause more energy to be released. Our outer layers are going to then expand at this point though and cool, and that will create a red giant star. Sometimes I put an in-between step here called a planetary nebula. Not the same nebula I was talking about here, which is a collection of high density gas. Planetary nebula, and it's not a planet either, having a core inside and a lot of these gases around it. Eventually, this red giant, my helium's going to run out as well. My core contracts, but not quite enough for a new fuel and to use larger nuclei. it is going to end up releasing those gases I was talking about, the outer shells. And this that's left behind is going to be a very hot, very dense core called our white dwarf. If I look at the Hertzsprung diagram, it's going to be in the bottom left. Now, what if our main sequence star was bigger than 8 times the mass of the Sun? I'm going to have a different process. Because similar to making the red giant, I'm still going to get my core to shrink. But in this case, because it has a bigger mass, I'm going to be able to create a high enough temperature to actually fuse elements up to iron. But eventually it will run out as well. And when its outer shell blows away, instead of us talking about the planetary nebula, now it's going to be blown away much more violently. So that outer shell eventually leaves, and what we're going to get is this supernova. Now look again, we've got another difference here. Stars that were greater than 20 times the mass of our Sun would have gone from a main sequence star this way, and they are still going to have a core that's probably 3 times the mass of the Sun, even after the supernova. This pressure pulling them in is going to be so great that it collapses into what we call a black hole. This is black not because it doesn't have any color, but because everything is being pulled into the center, including light. When we don't have light coming to our eyes, we call it black. If we have a core that's less massive, then we can still have the outside leaving from the supernova, but what we're going to be left behind with will be called a neutron star. So let's look at some of these examples. And to be honest, I would keep that diagram that we were looking at in our mind as we structure our answers. Outline, that's a level 2 question, so not just straightforward like a state, but not necessarily as detailed as a explain. Why a main sequence star has a limited lifetime? Well, let's start off with what is it using as a fuel. A main sequence star uses hydrogen as a fuel, of which there's a limited amount. As it's used up, the rate of fusion will decrease, and that affects the outward radiation pressure. This is going to affect its stability, and that will change the type of star. Sorry, my handwriting is very awful today. I would suggest that if we were asked this would be a 3-mark question. 1 for telling me why we have a change happening. We're using up all the hydrogen. 2nd, well, what does that affect? The rate of fusion affects the radiation pressure, and then finally, that affects its stability, and then it's not going to be a main sequence star anymore. If there was a 4th mark, I would say you would go on to describe whether it was going to become a red giant or a super red giant, depending on the mass. In part B, outline the conditions needed to create a red supergiant. So first we're going to have a main sequence star with a mass greater than 8 solar masses. It's going to need to run out of hydrogen. At this point, the core will be able to fuse up to iron, and we will consider this a red giant. Example 2. At the end of the stable stage of its life, a star will change. Describe and explain the changes that could take place for a star in order to become a white dwarf or become a black hole. So first of all, I want to point out this stable stage implies a main sequence star. A star will typically spend up to 90% of its lifetime as a main sequence star. So remember, this is a different question from the first one, so I need to first set up what's going to have to be its mass in order to get to become a white dwarf. So it's going to have to start off with a main sequence star less than 8 solar masses. By the way, I would not write this point like this on a test or exam. I would actually write out main sequence star. So to become a white dwarf, we need to be less than 8 solar masses. It will next become a red giant before it becomes a white dwarf. At this point, its core is going to contract to become solid. It's going to release the outer shell. It's going to have a low luminosity and high temperature, and that will be the white dwarf. Now, in order for it to become a black hole, that means my main sequence star is going to be greater than 8 solar masses. It's going to be a red supergiant next. From there, it's going to eventually run out of fuel after making up to iron in its core. It's going to go supernova. And since we're going to have a black hole, that means the remaining core is going to be 3 times the solar mass to be a black hole. Now you can see with this question, I'm trying to say describe and explain the changes, which is different from the outline from before, and hopefully you can see the differences in my answers because of that. Well, I hope that's helped. Please read the success criteria one more time. I hope you can now say yes to both of these points.